All right, let's begin. Homework number 5 is going to be due next Tuesday, and that includes one hardycross method problem. I think a couple of you have already gotten started on that. After you get the spreadsheet set up from last time's example, I think you'll be able to sail through that. Then the other two problems are related to water hammer, which we're going to be covering in today's lecture. Looking a little bit further into the future, on Tuesday the 24th we'll have our first exam, and we'll do that during the lecture. And I'll have some additional details next week for you about the exam. Any questions about the announcements? Okay. If we've got the time, and I think we probably will, we'll take another look at that hardycross example that we were working on Tuesday. What we'll do is pull up the spreadsheet and compare the values that we got there with the simulation in water gems, just to see how the two answers compare. And I asked you to work on that example spreadsheet outside of class last time, and if you're continuing to not get it to converge, if you have any trouble, feel free to stop by and I'll help you troubleshoot. I've seen enough different versions of this spreadsheet that it's pretty easy to spot the errors at this point. So if you get hung up on it, feel free to let me know and I'll do my best to help you. All right. Well, just to introduce the concept of water hammer, I came across something online a couple of months ago where someone was asking, what's the most expensive mistake that you've ever made? And so it was, like a forum. People were explaining all the mistakes they've made in their lives. And here's one that was offered by, what's the username there? Dubfunking Steph. I don't know what that means, but let me give you a minute to read what their expensive mistake was. So, I don't know, at some point in our lives, maybe a handful of us will make $800,000 mistakes, but it sounds like this person got it over with pretty soon. Water hammer. So, this lifeguard, I guess, was not playing around. Part of their job duties was changing the valves on the pool, probably backwashing the filter or whatever, and in the process of shutting off the valves caused a water hammer. And in this case, because of the flooding and the ruptured main, it cost $800,000 to fix. So here's a picture of a really nice car that's flooded, just to drive home the point that water hammer can be expensive. Now, it's not always this enormous catastrophic loss. Sometimes water hammer can just be an annoying thing in people's house that they sort of scratch their head and wonder about what's going on. And that's what's going to be illustrated in these videos where water hammer is being observed in the home environment. So let's take a look at those, and then we'll move into the calculations that explain what water hammer is and how we can avoid it. Almost seems like his pipes are haunted, right? What is all that banging? You notice it's as he was closing the valve that the trouble began. Let's take a look at another one. Whoops.
It's a familiar sound. Nearly everyone has heard it in their own home when someone slams a faucet closed. problem.
I think it started the next one. All right. And it crashed PowerPoint in the process. All right, we need this one. Okay, watch the washing machine. Well,
Okay, you heard that noise come from the pipe. When we get closer, we're going to see the action over here. You see the whole pipe shape. That's from the cold water valve. And there's one solution to take care of this problem. Actually, you have two. You either lower down your house water pressure, or you have to get yourself one of this guy called mini water rester.
all right, we'll talk about what that device does, but what you saw in the video is that something about the washing machine is causing the pipe to shake, and that's not so bad if it's a flexible pipe like is connected to the wall, but inside the wall where the pipes are fastened, you know, to the wall, over time that vibration can sort of shake the pipes loose off of the supports, and then the banging gets even louder. So what was happening in the washing machine is that there's a valve inside the washing machine that opens and closes very quickly, most likely a ball valve. And we looked at valves in a previous class lecture, and we saw that a gate valve opens up very slowly. By contrast, a ball valve is just a sphere that has a hole through it. And when you turn it one direction, suddenly there's a path for the water to flow through. So in the case of this washing machine, it has a valve that's opening very quickly so that a little bit of additional water can go into the wash, and then it's closing very quickly. And in fact, it's closing so quickly that a surge of pressure is sweeping through the pipes. So let's step our way through the physical process that causes water hammer. And the easiest way to explain it is to envision a very large reservoir that is connected by a pipe, and at one end of the pipe is a valve. Pretty common to control the flow rate. So water is going at a steady state through the pipe towards the valve. You can see that in the diagram here, we're depicting the initial flow velocity of the water. And it doesn't matter if the pipe is inclined upwards or downwards, or if it's horizontal. The threat of water hammer is equal regardless of the pipe's orientation. The other thing to point out is that we have graphs of the energy situation in the pipe. And this horizontal line represents if there was no energy loss. And so H sub F is the energy loss due to pipe friction as water is flowing through the pipe. And so this dashed line is the energy grade line, and then the dashed line below it is just the pressure and elevation heads. And so that's the hydraulic grade line. So water is flowing freely at steady state towards the valve, and what we're going to do is we're going to focus in on just one section of the pipe that's immediately upstream of that valve. We'll put a control surface around it and consider the flow in and out of that boundary. And as we consider that control surface, remember back into fluid mechanics the idea of momentum. And when we were doing labs back during fluid mechanics, we had the jet impact lab, where we were putting all of those heavy brass weights on top of the jet impact apparatus, and then we'd turn up the flow rate of the jet, and the faster the jet was impacting into that deflector vane, then it could hold a heavier weight. And what we learned from that is that the difference in the velocities causes an increase in force that's applied to a surface. And that's what's going to happen here is as we begin to close the valve, there's a very slight difference in velocities between the flow that's going into our control surface and the flow that's going out. When we close the valve here, the water that's coming away, further away, is still moving at a faster rate than the water that's close to the valve. in general, water is incompressible, but there's a very, very small compressibility of water at very high pressures, and that's what comes into play when you close a valve like this very quickly when there's a long run of pipe upstream of it. So we suddenly close the valve, and when that valve is suddenly closed, then there's a pressure buildup in the vicinity immediately upstream of the valve. So you can see it's depicted here as these little dashed lines. And what that means is that because there's a pressure buildup immediately upstream of the valve, actually the pipe begins to swell and expand because there's so much pressure there that the flexible material of the pipe will bend just very slightly, and that pressure wave is going the opposite direction of the initial flow. So there's a lot of pressure here near the valve, more pressure than there is actually over here. And so the pressure wave is working back in the original direction of flow because it's going towards a low energy environment. There's just temporarily more energy near the valve than there is inside of the reservoir. And so this delta H is depicting the extra energy that accumulates upstream of the valve because of the pressure buildup. So one way to think about it, why that pressure is there, is in terms of momentum equation, which you remember from fluid mechanics. And the other way to think about it, and also a contributing factor, is convective acceleration, that the velocity is going towards the valve initially, and as we're closing the valve, the flow rate is decreasing. So remember that if the flow rate is going this way, but the velocity is decreasing, that means there's an acceleration to the left. And so if there's an acceleration to the left, what convective acceleration tells us is that there's a pressure increase in the opposite direction of acceleration. And so there's more pressure here than there is over here. And so the pressure accumulates on the end of the pipe that's nearest the valve because of the deceleration of the water. Now, there's an important term here that we'll start to use, and that is celerity. Celerity, sometimes this word is just used interchangeably with speed. Like in common language, celerity can just mean speed. But in hydraulic engineering, we use celerity to describe the velocity that a pressure wave has as it moves through water. So this pressure wave goes back towards the reservoir at the speed of celerity, which is just the pressure of a shock wave going through water. It's similar in concept to the speed of sound. You know, the sound barrier when a plane is going Mach 1. There's the shock wave that propagates through the air. This is the speed that a shock wave propagates through water instead.
So it's constant?
Well, that's a good question. Actually, celerity depends on the environment that the shock wave is in. Just in free and open water, celerity is constant, assuming constant density. But when we confine water in a pipeline, then we have to calculate a modified celerity. And we'll do that in an example where we have a certain pipe that water is flowing through, and so the velocity changes because of that. That's a good question. Are there any other questions before we move on? Okay, so at this point, you know, we're stepping through the process. At this point, this snapshot, the shock wave is still moving towards the tank. It's not all the way there yet. The shock wave is, you know, only through this section of the pipe, and it's still going back towards the reservoir in its initial reflection, because actually it's going to bounce around several times, and so it's just on its first return trip to the reservoir. You know, here in the box, I've reminded you that the compressibility of water is very low. You know, it takes a lot of pressure to compress water, but in the case of a water hammer, we achieve so much pressure that the water is compressed a little bit and the pipe walls expand. So now in this snapshot, the pressure wave has made its way all the way to the reservoir. And we're in a temporary equilibrium right now, actually. The pressure wave got to the reservoir, and at this instant in time, the pipe has expanded. So you see this little dashed line. That's representing the fact that the pipe is expanded just a little, not really a lot, but enough that there's more water inside the pipe than there used to be when the pipe wasn't expanded. You know, think about if the pipe sort of swells just a bit, then it's going to have more volume that it can store. More water is going to be found in the pipe than when its diameter was a little bit smaller. And so actually the liquid height of the reservoir can decrease a little bit when the pipe is swelling. The water level goes down just ever so slightly on account of the additional volume that's stored inside the pipe. And the pipe actually has a lot of energy in it because it's got potential energy of that pipe that has expanded. It's going to contract again. It's just a temporary thing that it's expanded because it has so much energy inside the pipe. That energy is going to flow back towards the water is going to flow back towards the reservoir because it's expanded. And so now that's what's depicted here, is that the water that temporarily had flowed into the swelling pipe is now going back into the reservoir, and we have the shock wave returning back towards where the valve is. And so in our first stages, the shock wave was going towards the reservoir, and now it's making the return trip back towards the valve. So this wave can move back and forth between the valve and the reservoir several times before it finally, the energy dissipates enough that the water hammer is finished. So any questions about why there's this banging that we hear? You know, the frequency of the banging when the guy was closing his valve, that actually means something. There's a speed that the water is traveling, and how quickly you hear the banging indicates how far the water is traveling before how far the shock wave is traveling before it finally reflects off something and is coming back. So it's all about wave reflection. And water compressibility is an important part of calculating water hammer. And you know, we've talked before that it really takes a lot of pressure to compress water. And here is an illustration of that effect that I took from the website of London South Bank University. And it shows the temperature dependence of water compressibility. And you'll notice the units here are inverse gigapascals. And the reason for that is it is a unit change in volume. So that would mean, you know, how many liters are compressed out of a certain volume originally, also measured in liters. And so the change in volume is unitless because it's a change in volume divided by the original volume divided by pressure. And so what we're left with is these units of inverse pressure. And gigapascals is way, way far beyond the water pressures that we're usually working in. In a typical municipal environment, remember, 500 kilopascals would sort of be like a baseline pressure, water pressure for inside your house, 500 kPa. And so beyond that is MPa, megapascals, and then 1,000 times beyond that is gigapascals. So it really takes a high pressure in order to change the volume of water. And when you do apply that pressure, why is it changing volume? It actually has to do a little bit with not the molecule itself, but the association that the molecule has with adjacent water molecules. And so it comes into these sort of associations with adjacent water molecules that very slightly have different volume requirements. And these different diagrams give you an idea of some of the different shapes and arrangements that water can take on as it's being compressed. So this was compressibility. The inverse of compressibility is actually what we'll put into our equations. So sometimes compressibility makes more sense to students because we're thinking about change in volume relative to how much pressure is applied. But it's actually the bulk modulus of elasticity that goes into our formulas for celerity and the amount of the pressure that accumulates. And bulk modulus of elasticity, you'll see, has, instead of volume divided by pressure, this is pressure divided by a unit change in volume. All right? So it has a negative sign here, which tells us that an increase in pressure is going to decrease the volume that is occupied by a certain amount of water. So that's why we have a negative value for the formula for bulk modulus of elasticity. And you may remember bulk modulus from your materials classes, because it's a physical property that can be applied to solids as well as liquids like water. Here's a table that's taken from the text. It shows that the bulk modulus changes according to the pressure of the environment that the water is in, but also according to temperature. And so when we do problems like this, if we really want a high degree of precision, we have to specify what's the original pressure that the water is experiencing when the water hammer begins, and then also know the temperature, whether it's room temperature or something else. So here's the bulk modulus in SI units, and here they are in traditional units. Of course, traditional units are always a little tricky, and even more so when we're going to be working in examples with water hammer, because we have the bulk modulus given in terms of pounds per square inch. But when we do our calculations, we're going to need to remember to change pounds per square inch into pounds per square foot. So what's the conversion from pounds per square inch and pounds per square foot? 144, yeah, because there's 12 inches in a foot, and it's 12 inches on each side. So if we have 1 pound per square inch, then that would be 144 pounds per square foot. So just as a hint, when we get to the example, we'll work the example in traditional units, and you'll need to remember that conversion factor. All right, so we talked about celerity, and it's not celery, but every time I say celerity, I think of celery. It means basically the velocity of a pressure wave. And theoretically, out in the open water, we can calculate how quickly that pressure wave is moving just by considering the bulk modulus of elasticity and the density of the liquid. All right, so bulk modulus, of course, that depends on the pressure and the temperature. And the density of the water, that also depends on the temperature of the liquid. But a typical open in the environment celerity would be 4720 feet per second. So it's really moving quickly, much faster than a shock wave moves through air. But in a confined pipe, we have a different equation for the speed that a shock wave moves through water. And it accounts for the diameter of the pipe, and the diameter is the inside diameter that we're talking about, because we know a pipe has thickness, and the pipe thickness is accounted for here. The thicker the pipe is, obviously, the less it's going to flex. And so we have to remember that it was the pipe expanding a little bit that caused an accumulation of energy inside of the pipe. And so we have to know, how is the pipe going to behave when there's a pressure accumulation inside of it? And so the pipe's behavior is described by its thickness and then the bulk modulus of the material itself. The bulk modulus of the material says, how well is this particular pipe going to expand when there's an increase in pressure? So here the celerity in the confined pipe takes the water characteristics and the pipe characteristics into account. And that's how we find how quickly the shock wave is moving through the pipe. And so if we know the speed that shock wave is moving through the pipe, and we know the pipe's length, then we can find the travel time for some pipe length. Now, this formula that I've given you, though, is just the travel time. It's a one-way travel time. It's going to turn out that operationally, what we need to make sure of is close the valve slow enough that the shock wave can go from the valve to the reservoir and back before the valve is closed. That's what we can do to prevent the library from flooding and an $800,000 repair to the city's water main. We have to make sure that we close the pipe nice and slow, because if you close the pipe slow, the pressure doesn't accumulate, because the acceleration, or rather the deceleration, is so slow that there's not a pressure accumulation. So that's really the key to all of this, is rather than just snapping that faucet closed really quickly, you close it slowly and the pipes aren't going to vibrate. So the travel time that we have to consider is the round-trip travel time. And once we know the velocity that the water is traveling initially and the speed that it's traveling, you can actually find out how much the pressure is going to increase during the peak of that surge. And here's the formula for that. Now, as I've mentioned, the worst case scenario, you're going to get the most pressure accumulation and the worst water hammer if you close the valve so quickly that it's totally closed before the shock wave makes it to the reservoir and back. So that's the worst case scenario, and that's what's going to give you the maximum pressure increase. And if you close the valve slower than the travel time takes to go there and back, then you won't see that delta P. You'll get a pressure less than that delta P. All right, so here's the example where you're going to get a chance to try these equations out. We have a system that's described here, a 2,000-foot long pipe. The 4-inch steel pipe that we're talking about here, that's the inside diameter. And so that's what you can use to get the cross-sectional area. And you're going to need the cross-sectional area to calculate the velocity, the initial flow velocity. Here we've got the characteristics of the pipe, the thickness of it, and the bulk modulus of the pipe material, since this is based on steel, this bulk modulus. Here's the flow rate, 0.6 cubic feet per second, and then here are the water characteristics. We have the bulk modulus of the water and the density of the water. And you know, traditional units, the density is a bit weird, 1.94 slugs per cubic feet. And I remind you down here at the bottom that if you have one slug being accelerated 1 foot per second, then it takes 1 pound of force to do that. So you'll need this conversion factor at the very end. So I'd like you to go through these equations and first of all, calculate the pressure increase if the valve is closed instantaneously. And by instantaneously, what we really mean is it's closed so quickly that the pressure wave, it's closed by the time the pressure wave makes it back on its round trip. And then after you've found that pressure increase, let's try and avoid the water hammer from occurring and calculate the minimum amount of time that should be taken to close the valve. All right, so as you work on this example, feel free to collaborate with your classmates. That's always welcome on these. And then once you get a bit of a head start, I'll start putting the solution up on the board. I didn't necessarily need to make it my first calculation, but I found the initial flow velocity at the beginning just because I knew later on I was going to require it. So we've got the flow rate divided by the area to get the initial velocity. And you know, 6.87 feet per second, that's a typical speed of water flowing through an underground pipe network. That's not unusually high. And 2,000 feet isn't an unusually long stretch of pipe. You know, throughout the area here, there are water tanks all over in the hills pressurizing water in different neighborhoods, and it would be very common for there to be 2,000 feet from a tank to a customer. So, you know, we're not dealing with really crazy values here. This is a pretty accurate example. So we can find the velocity of the pressure wave moving through open water for the temperature conditions that we're describing. You know, using this bulk modulus, 4874 feet per second. But when we find out how quickly the pressure wave is moving through a pipe, we see that the velocity is reduced slightly. And that's because as the water is moving through the pipe, it's also causing it to expand. And so you could think of it conceptually as it's doing work in two ways. The water, the pressure wave is moving forward, but it's also causing the pipe to expand. And so it's that expansion that slows it down a bit. And that's why we were taking into account the diameter of the pipe and the bulk modulus of the pipe material. Is there anything in the calculation here or what you did that was confusing as you were calculating C that you want to clarify? So here's the maximum pressure increase, 407 pounds per square inch. When we go through and we multiply the density of water by the speed and the initial velocity and convert it from slugs into pounds of force, and from pounds of force per square foot to pounds of force per square inch. Now that's a lot of pressure. That's around, since we've been trained to think in SI terms, that's around 2,800 kPa. So what's a typical water pressure in a pipe network? 300, 500. Like at the upper limit, because water heaters are kind of sensitive to high pressure, it's often suggested that 850 kPa should be an upper limit for water pressure, because beyond that, valves start to leak. And so this 2,800 actually, you know, that could blow some seals. Someone's water tank could explode, and hot water everywhere, not a good thing. So this is definitely, this situation could do some damage if the valve is closed too quickly. So how quickly should the valve, what's the maximum, the minimum amount of time is 4,000 feet is the round trip distance from the valve to the reservoir and back. And it's going to be moving the shock wave at a speed of 4397 feet per second. So that means that 0.91 seconds. When the valve is closed, it should be closed in greater than 0.91 seconds. So if this is the kind of valve like a globe valve that you can just slap it shut and instantly the flow is off, then let the fun begin, because there's going to be the water hammer. But if it's a gate valve and you got to crank it for that gate to finally close the opening, then probably things will be fine.
So literally preventing this power issue is just a matter of turning valves.
Yeah, exactly. And or which valve you use, exactly, because there are some valves that it's hard to close a gate valve quickly, but a globe valve you can close quick. But yeah, all you have to do is close the valve slow. And we saw that little plumbing device the guy was saying. It's kind of like a shock absorber for water hammer when it occurs. And we'll look at a surge tank. Yeah, that shock absorber takes some of the energy out so that when the surge occurs that it's got somewhere to go rather than banging and flopping the pipe around. But that's not always an option. It's a little washing machine can have one of those little shock absorbers, but a big, gigantic, let's say, water flowing through the Hoover Dam, they're very careful about how quickly they close valves at the Hoover Dam. There are computer systems that have been designed with the sole purpose of making sure that valves don't close too quickly. So, yeah, it's a big problem with a very simple solution. That's right. Yeah, that's why we've doubled the distance. Yeah, so half of T would be the one-way distance. So you're saying, now, if you close it before this, then yes, you'll get a water hammer. If you close it, let's say it takes you 2 seconds, you may still get an increase in pressure, but it won't be the maximum delta P. This delta P is associated with this time. But even if you close it slow, there can be some increase in pressure. So who's going to be paranoid as they turn off the faucet tonight? Try and get the water happen. Yeah, definitely. Especially if you live in the dorms and it doesn't matter, right? All right. So, surge tank. This is another one of the options to prevent the damage that can occur. And I'll go through this calculation fairly quickly so that we'll have some time left over to look at the example from last time that we were doing with Excel. But a surge tank, what it does is rather than allowing the pressure to accumulate and the pressure wave to reflect back towards the original source of water, there is a relief tank here, and the increased pressure, instead of causing the pipe to expand, it takes a lot of energy for that pipe to expand. It takes a lot less energy for the water levels just to rise here, where it's only working against atmospheric pressure above it. And so the purpose of a surge tank is just to provide an outlet so that the surge never causes damage upstream. And we can size a surge tank, and you'll do this in the homework. You'll size the surge tank depending on the cross-sectional area of the pipe length between the valve and the reservoir, and then it also takes into account the cross-sectional area of the tank. So the bigger the tank you've got, obviously the lower the increase in water depth is going to be. There's just a certain volume of water that's either going to be trapped in the pipe when the pipe starts to expand, or we can have that volume of water that would have flowed into the pipe during the expansion of the pipe. We'd much rather just have it in the surge tank. So we can either have a tall surge tank or a wide surge tank, but there's just a certain volume of water that has to be accommodated inside of the surge tank. So let's consider the same situation. We've got the 4-inch pipe that we had before. The pipe length is 2,000 feet, and lo and behold, we've got the initial flow velocity of 6.875 feet per second. So if we were going to try and make a surge tank to prevent water hammer, and we want it to have a maximum depth of 1 foot, how big should the diameter of that surge tank be? Well, let's start off with our formula. S max is V naught times A times L divided by A sub T times G to the 1/2 power. Okay, we're going to rearrange that. What we're trying to solve for here is the tank area. So the algebra required for that, we've got S max divided by V naught squared is equal to A times L divided by A sub T times G. And finally, A sub T is A times L divided by, in the denominator now, S max divided by V naught squared times G. Okay. Our tank diameter that should be used if the allowable surge depth is 1 feet. So let's put in the values here. A sub T is going to be the area of the pipe, and the pipe area of the pipe is pi times 4 inches out of 12 to get it feet squared divided by 4. The pipe area is 0.08727 square feet. So that's what we're going to put in here. This A is referring to the pipe area because we're trying to find basically what's the volume of water that would be going into the tank that otherwise is going to be in the pipe. Okay, so 0.08727 square feet times 2,000, which is the length of the pipeline. Now, we're back to just the one-way length. This isn't the round-trip length. Divided by 1 foot is the maximum surge depth that we want, and we've got 6.875 feet per second. Square that, and then G in traditional units, 32.2 feet per second squared. Okay, so the tank area is 256.2 square feet, and the diameter, therefore, is 4 times the tank area divided by pi. You know, here, in this formula, I've just rearranged the cross-sectional area formula to solve for D. And so it's 4 times 256.2 square feet divided by pi to the 1/2 power. That tank should be 18.06 feet in diameter. That's a pretty big diameter tank. Rather than make a surge tank that has that big of a diameter, it might be better to revisit the requirement that the allowable surge depth is limited to 1 feet. Maybe it would be better just to have it higher than that, and then we could reduce the diameter of the required surge tank. But as long as we provide a place for the water to flow into near the valve, then there's no problem. Of course, we may not want to have the water open to the atmosphere in the vicinity of the valve. That could be an issue, but anyway, any questions on the surge tank? Yeah, it has to be close to where the valve is that's going to be closing. Otherwise, the pressure will still accumulate. The further away it is from the valve, it just becomes basically another reservoir. So, you know, if it was halfway between, if it was like in the middle of the pipeline, 1,000 feet from both the main reservoir and the valve, it would provide some protection because now there's only 1,000 foot of distance between them. But the closer it is to the valve, the better. All right. Let's revisit this hardycross example that we were working last time. How many of you got a successful spreadsheet that works? Okay, maybe a third of the class. How many of you worked on it, but there's an error somewhere and you don't quite know where yet? All right, and so I guess the balance is people who didn't work on it, right? But you will, because you've got the homework coming up. Here's the solution, and we didn't get to talk much about how the pressures were calculated. So before we switch over to the water gems solution, just for purposes of comparison, I thought I'd explain again how to calculate the pressure, because that's going to come up in your homework assignment. All right. We just know it's given that the pressure at A is 600 kilopascals. Okay? They measured that, and so be it. The pressure at A is 600 kilopascals. What I've done here is I've calculated the head at A. And the head at A is simply the pressure at A divided by the unit weight of the water. And so we had 600,000 newtons per meter squared divided by 9810 newtons per meter cubed. Okay, so that's where 61.162 meters comes from. This was a calculated quantity based on the pressure. For the rest of them, though, it's kind of the other way around. I'm calculating the pressure based on the head. So let's just take, for example, B. Okay, we know from our analysis, if we look up here into the flow rates, AB is a positive value. Okay, so clockwise is positive in this loop, so AB is flowing from A towards B. Is the pressure at B going to be bigger or lower than the pressure at A? It's going to be lower. Otherwise, the water wouldn't be flowing from A to B. The only way water goes from A to B is if there's less head at B. And so what we know is the head at B is however much head there was at A minus the pipe friction between A and B. And luckily, that's something that we calculated here in the spreadsheet. We have the head loss between A and B. So the head at B is 61.162 meters minus 3.49. And that's where this 57.672 comes from. Okay? And now the pressure, now that I know the head at B, the pressure at B is just the head at B times the unit weight of the water. So it's the inverse of what I did at the first junction. And so all of these heads are just, we started where we knew the pressure, and we're either increasing if we're going against the flow, or decreasing if we're going in the direction of flow. So the head at F is going to be head at A minus whatever losses there are in pipe AF. What about when we get here at C? So you can see we've got some pressure at C. Now we're going against the flow direction, so that means that the pressure at D has to be higher than the pressure at C. It's going to be whatever head we had at C plus the losses through the pipe. And you'll notice that here, the head at D is in fact a little bit higher than the head at C. So that's how you, once you've finished the iterations, and our convergence criteria are that the flow rate change is about 1% or less. Here I did 4 iterations. If I'd done a 5th iteration, this one pipe where the flow change was greater than 1% would probably be under 1. You know, these low flow pipes are the last ones to converge. And we'll see that actually, it's the low flow rate pipes that give you the most trouble. Also when we pull open the water gem solution. So any question about the spreadsheet, anything you wanted to go over wasn't clear when we were working this last time? All right, you had some exposure to water gems when we were in fluid mechanics last semester, and you're going to have a lot more this semester. I'll send a reminder email with all of the server details and the school code. So I'll send you the information you need to be able to download the software onto your own laptop. But what I'd like to do today is just set up this same problem in water gems and see how well does the flow information that we got with our spreadsheet, so how does this flow information compare to a network that we could put together with water gems? We've got 15 minutes and I think that'll be plenty of time. So this will be a good refresher of how to use water gems. We got to start a new project, and the first thing we're going to want to check is what are the units of the project. We need this to be in SI units because all the given information like the pipe lengths and pipe diameters are in SI. So I go into Tools and check the options to make sure that the units are not in customary but in SI, and click OK. Now that I've changed it, I need to close it and start a new project, because the previous project units would somehow stay, and check units SI. Okay, so we're good there. And the other of the two preliminary things you always need to remember to do is go into the calculation options and make sure that it's set to the Darcy-Weisbach equation instead of Hayes and Williams. Remember, Darcy-Weisbach equation is more accurate than Hayes and Williams. And we don't care if it's going to take a couple of extra iterations on the computer because we've got the time. So we've switched it over, and it's always a good habit to save your work. So let me create a temporary folder on the computer and save this. Okay, so I'm going to call this our Hayes and Williams check, and I've saved it. I'd like to have an image in the background that I can draw on top of. It just makes it a little easier sometimes. And in the project, you'll have the same thing. And I don't think that I taught you how to import an image when we were doing the preliminary testing of this program in fluid mechanics. And so down here in background layers, it's pretty easy. You just click New File, and then it gives you the chance to browse to whatever image you'd like to add. And I have this image that I created that is the same thing that we had from here. It's this same diagram that came from PowerPoint. Now, the way that I've imported it is not to scale. When you do the project, I'll give you a scaled image so that 1 pixel equals 1 meter. But right now, that's not the case, and so I'm going to have to be sure and go in and do user-defined lengths when I'm setting up the pipe characteristics. Okay, so now that this image is in the background, I'm just going to draw right on top of it. And so here is the way that you draw a pipe. I'm going to put a junction at A, junction at F. Actually, I'm going to go in order. A, B, C, D. Now, I can't do E next, but F, E. I need to make sure that C is connected, and then I think I haven't yet connected A and F. Okay, now let me just make sure that the lines are where they need to be. I can switch that on and off. My symbols are a bit small, and so I'm going to go in here to the options and change the symbol size, let's see, drawing, yeah. Symbol size multiplier to 5, and now you can see those little dots are there to signify a junction. Okay, so now what we have to do is make sure that the characteristics of the pipe are correct. I'm going to enter in the correct pipe lengths and diameters, but it'll actually make things easier if I rename the junctions. So I'm going to make my text height multiplier also 5. And so right now, the junctions, that's too small. Let me do 10 times bigger, and maybe we'll be able to see things here. All right. So now we can see the labels of things. It's called J1, J2, J3. I just want to give it the same names that it had when it was, in this example, how we had A, B, C, and so on. So when I go into the pipe table, I'm going to change the labels so that we've got A, B, oh, I'm sorry, not the pipe, the junction. Yeah, the junction table. All right. A, B, C. I got to make sure I'm doing the right ones. D. Now, junction 5 is this one. I think that's F. Junction 6 was E. All right. So they should all be labeled now. I still would like those to be a bit bigger, so I'm going to change this up to 15 so the text size is larger. It's starting to get big enough. All right, so now I've labeled the junctions. It'll be a little bit easier when I get into the pipe table to know which pipe I'm working with. So, you know, if the start node is A and the stop node is B, then this pipe is going to be AB. This pipe will be, I'm naming the pipes just what the start and stop node are. BC, CD, DF, EF, CE, and AF. Okay? So they have the correct names now, and I need to make sure that the diameters and the lengths are correct. And so AB had a diameter of 500, BC. And by the way, check the, as I'm putting these characteristics in, follow along in the spreadsheet to make sure I don't key in incorrect values for the diameters. 650 is the diameter, 850, DF, 500, EF is 700, CE 600, and AF is 400. Okay, we also need to make sure that the lengths are correct, and you'll notice that the scaled lengths here don't match the actual lengths that they're supposed to be because I didn't import the image so that 1 pixel was equal to 1 meter, and so I want it to be user-defined length. So I'm going to global edit so that we have yes for that, the user-defined length. Now that allows me to enter in these user-defined lengths. So AB has a length of 220 meters, BC is 100 meters, CD 80, and so on, DF. EC 150, and AF 180. Okay, the only other thing I want to double check is the material type, because in the example it said all pipes have a KS of 0.3 millimeters. And so I can turn on the Darcy-Weisbach. I'm sorry, not the Darcy-Weisbach, let's see. If I go into the material properties, we can check to see what it's assuming. And if I use, for example, concrete pipe, here is the roughness height of concrete pipe, and we need a K-sub-S of 0.3 millimeters. So right now this is 0.1 millimeters if it was concrete pipe. But if we change it all over to cast iron, so if we global edit to cast iron, then that will give us the roughness that we need for each of the pipes. All right. How are we going to make pressure at A 600 kilopascals? How do you specify a pressure? Any ideas? Do you remember what we did? Well, it's not in the junction table. We were putting down something in fluid mechanics to cause pressure. Do you remember we had pipes connected to something? It was a reservoir, right. If we have a reservoir with a certain water height, then that pressurizes that junction. So we need to actually put in two reservoirs. I'm going to put in a reservoir here because I've got water flowing in from the reservoir. And I'm going to put in a reservoir here because water is flowing in. It has to come from somewhere. And the reservoir elevations that I'm going to specify are, we're double checking this Excel solution. The reservoir elevations are going to be the heads that it's picked here. And so at A, I'm going to say the water elevation is 61.16. And at D, I'm going to give it an elevation of 57.83. Okay, so let me just double click on that reservoir. And here's the elevation of the reservoir. I want it to be at 61.16 for that one. And this reservoir should be at 57.83. I need to connect the reservoir to the networks also. So I'm doing that. And since the reservoirs aren't actually in our original solution, we just put these in to cause the pressure and to provide some place for the flow to come from. I want to make sure that these pipes are very big so that there's no energy loss through the pipe. So I'm going to make the pipe unusually big from these imaginary reservoirs that only exist for us to force the pressure condition that we want to check. So I'm going to open up the pipe table. And for these two new pipes, I'm going to make the diameter 2,000 millimeters, just so that there's no question about too much energy loss through those pipes. And you'll do the same thing in the project. You're going to want to make sure that you have really big pipes when it's connected to a reservoir. Let me save my work. The only other thing I need to do now is I need to specify the demands. And so water's coming out at E and B. I go back to the junction table, and at E, I want there to be a demand collection. That's how we specify the flow rate. So E should have a demand collection of, how much is going out there at E? Okay, so 1,600 liters per second. And then at B, there should be 600 liters per second. Okay, and I can close that. Now I think the system has everything it needs to know in order to calculate. It knows the pipe characteristics like the length, the roughness, and the diameter. It knows the pressure at the control point. And the system knows, it assumed 0 elevation for everything. So when I was putting in the reservoir elevation, that was above sea level, and the junctions are assumed to be at sea level. Since, it's just the default elevation is 0. So when I calculate it, oh, great, the license is expired. Luckily, I have this on my office computer. So let me just remote into my office computer, because I know that the license isn't expired there. And I'll show you what I came up with. We've got 1 minute left. That's all it'll take. When I was working on this earlier, I actually did the annotations as well. So how good is the guess that we had with Excel? It turns out to be pretty good. Just let's pick a couple of junctions. Here at F, Our Excel solution said it should be 533.2 kPa, and at F, that's not F, here's F. It turns out to be 533. Let me zoom in. So 533. The flow rates are all good. It all matches except for the one pipe where the flow rate is pretty low. And those are always going to be subject to a lot of error because the flow rate is low. So I'll post a copy of this file in MU Online if you want to load it up and just make sure that you're getting Bentley to work okay.
Which pipe had the really low?
The really low flow pipe is BC.
Was that random or for a
BC.
specific reason?
No, it's just because there was more resistance there than the other routes, and so, in equilibrium, less water's flowing through it. All right, so I'll post this in case you want to open up water gems. It'll be in MU Online, and if you have any questions on the homework over the weekend, just feel free to send me an email. See you Tuesday.